Hey, hi, I'm Thomas Edwards. I'm a solutions architect working at Amazon Web Services in media and entertainment. And I'd like to recognize my co-authors on the paper, Vincent Troussart from Grass Valley, Willem Vermoost from the European Broadcasting Union, and Sithadev Vienku from Riedel Communications. And I'll say, MXL is definitely a group effort, and I really appreciate my co-authors on making a great paper. Please feel free to read it. Today, I'm not going to go too deep into the gory technical details of MXL. The paper does that to some extent. But what I really want to do is communicate the motivation for MXL, what MXL generally is, and then what the status of MXL is. Two years ago, the European Broadcasting Union, which is a membership organization of over 100 public sector broadcasters in Europe, and even some in North America, like the Canadian Broadcasting Corporation, developed the concept of the Dynamic Media Facility, or DMF. Now, their members are facing significant rapid change in the broadcast media industry, right? It's hard to say what's going to happen 2-3 years down the line. So they would like to have production spaces that can be used for any type of production. They'd like to have flexible control rooms for different productions types and different sizes. And they'd like for all of that to be running on software media functionality, dynamically reconfigurable software-based infrastructure, containerized, of course, for fast spin up and spin down. And they'd like that all to be running on commercially available generic compute, whether that's on-prem or whether that's in the cloud, or perhaps a hybrid of both of those. So within the layered architecture that they developed, there is the media exchange layer, the MXL, and that's what we're going to be talking about today, how software media functions can exchange media within the dynamic media facility. So if we look over the last 50 years of microprocessor progress, we found CPUs keep on adding transistors and cores, and that still seems to be going up with Moore's law. So that's really great. We've got super powerful processors now. But one of the things that happened in the early 2000s is that the clock speed of CPU cores hit an upper limit at a couple of gigahertz, and it's been stuck there ever since. So this affects the ability for software to have accurate timing for things like emitting packets onto a network. So that's a problem that we need to face. Now, let me talk about the history. So if you go back to the late 1990s, SMPTE invented HD-SDI, the carriage of uncompressed high-definition video over coaxial cable with a 148.5 megahertz clock sample rate for 10-bit samples, and the maximum allowed jitter was only about 10 picoseconds. Now you might wonder why have such a tight jitter level. In the late 1990s, RAM was very expensive. You couldn't buffer up flows with different latencies in order to do the switching. You wanted to have them switch as the raster was being painted in the exact same location on both the video flow you're leaving and the video flow that you're switching into. And there was no way that software was going to be able to achieve that kind of 10, 20 picosecond accuracy. So everything was bespoke hardware for the broadcast industry. And I think if you've noticed this week, occasionally it pops up, the screen goes black, it says SDI. That's because we've probably jumped out of the jitter buffer for SDI, right? It's very tight. So that wasn't going to work. So then in the 2010s, SMPTE developed SMPTE 2110-20. This is the carriage of uncompressed video, again, 10-bit 422, but packing a group of pixels into a UDP packet and sending that out over the Ethernet and IP network, maybe like 3 or 4 packets per line of video. So this enabled us to kind of back off the timing requirements a bit, but unfortunately, SMPTE 2110 really had to continue to interoperate with an HD SDI world. So we put these limits on the timing about a microsecond or so, well, plus or minus in terms of jittering. Now, at the time, many people, including myself, thought, oh, okay, no problem. Software can handle a microsecond accuracy timing. As it turns out, because of that clock frequency issue that we discussed earlier. No, that's not true. SMPTE 2110 is always implemented with FPGAs or specialized network processing units on specialized network interface cards like ConnectX cards, for instance, from NVIDIA. So we did not get to software timed transfers with SMPTE 2110 either. So that brings us to MXL, the media exchange layer. Let's embrace asynchrony. Let's have frames be able to be processed as soon as they're ready. There's no point waiting. They can be sent whenever they're ready. So this means our timing tolerances have gone from picoseconds to microseconds, and now we're milliseconds. And software can definitely time milliseconds. That's not a problem. So that gets us to the capability of software. Oh, let's do it. Did I do that? No. Anyway, I see the ghost of SDI is coming for me, man. So that gives us to the media exchange layer. So in 2024, we set up the first meeting of the group, which would come together and put together the media exchange layer software development kit. Met at EBU headquarters in Geneva. A bunch of different broadcast vendors showed up, different broadcasters showed up, different technology providers like AWS, NVIDIA showed up, and they are now all involved in an open source project. It's led by the European Broadcasting Union and the North American Broadcasting Association, but it's under the Linux Foundation open source project on GitHub. We've got representation from many, many companies across the broadcast industry and the Technical Steering Committee and the Requirements Council, and other folks are participating and adopting the technology. So let me talk about what MXL is and what MXL isn't, and this will really tell you what we're talking about here. It's for virtualized, containerized software media functions. It's not just for hardware like SDI or 2110. It's asynchronous. It's got looser timing that works with software. It can even be faster than real time in the workflows where that makes sense. Like if you're just applying a graphic to something, that doesn't have to take 16 milliseconds, a whole frame time. You might be able to do that in 2 milliseconds, and then that frame is ready to go to the next stage in the pipeline. So it's not synchronous like SDI or semi-synchronous like 2110. It's open source. It can be trusted by multiple vendors, and there's great observability into the code. You can see exactly what's happening. It's not a proprietary binary, which, by the way, might be owned by your competitor, and who knows what's in there. It is an SDK. It is code, so it's not a written textual specification or standard. The fact that it's SDK, it's code, you download it, you put it into your project, it means that interoperability comes a lot easier. I'm not going to say we don't have any problems, but it's going to take a lot less time to get MXL working together than, say, it took SMPTE 2110, 3 or 4 years for everyone's implementation to successfully work together. It's a small library with clear achievable goals, and it can be flexibly orchestrated. It's not some huge overarching framework that can do everything but reduces your flexibility at the end of the day. It's good for both on-prem and on the cloud. It's not good for just one or the other. And it's uncompressed, because uncompressed is the best. There is no argument about uncompressed quality. There is no argument about codec latency with uncompressed. And to top it all off, there are no concerns about intellectual property or codec royalties. It's based on the BBC R&D model of flows and grains. So a grain is a time-labeled sample of media, and a flow is a sequence of grains. And we're going to add on top of that the concept of an MXL domain. A domain is a collection of flows which will be used in a specific workflow. So here's the basics. So if you only take one thing away from this talk, it's this slide. This is what MXL really is at the end of the day. Media is exchanged between containers using shared memory. So on the same host, that means we have a tempfs file system and RAM on the same host. You read to it, you write from it. Going between hosts, we're going to use a libfabric abstraction is a common method to provide remote direct memory access, RDMA. And RDMA is when a network interface card reads from your memory, spits the data over the network, and the network interface card at the other side spits it back into memory at the other host. It does not involve the CPU. The CPU asks for it to happen, but the CPU is not actually moving the data. It's all direct memory access from the network interface card. Fastest way to move data between two hosts. That's coming soon. We don't quite have that yet, but we're just on the edge. The TempFS has all of the POSIX fine-grained security that you expect in a Linux-style file system. Read and write for users and groups, access control lists, so the security is already kind of baked in. Containers bind to those RAM volumes onto their local file system. And the initial essence formats, which we'll be supporting, include for video, V210, which is a specific way of packing uncompressed 10-bit 422 video into 8-bit bytes. It comes from the QuickTime libraries. We'll be using the IEEE 32-bit float audio. Again, the vendors who are involved say, well, this is what all of our libraries use already, so let's use float 32 audio. And for ancillary data, we're going to adopt the payload in SMPTE ST2110-40 that works well in the 2110 world, so if it ain't broke, don't fix it. MXL flows, they're just files at the end of the day. We have the concept of a ring buffer of a flow, and that's just a single fixed size buffer, and it's used as if it were connected end to end. So that way, as the frames come in, you're not using all of your memory, but at some point you're going to wrap around to have a limited amount of memory. A lot of the workflows that we've been doing in tests, it's 4 or 5 frames. It's really not that large. The good news here is that you can have multiple readers and writers accessing that ring buffer if you want to. The flow is a directory, and the grains in the flow are files in the directory. Pretty simple. So at IBC 2025, there are a large number of different multi-vendor MXL demos going on. And you just take a look at some of the different well-known vendors who are involved. I specifically was involved in the cloud interop. In our cloud interop, we had Riedel Communications, we had Matrox, we had TVU Networks, and all of them were sending video to a Grass Valley AMP. And you can see the Grass Valley AMP multi-viewer up on the screen. Again, this is pretty simple. Everybody just sent me the containers. I fired up the containers on EC2 instance, and they all were talking together using that TempFS RAM volume. No problem. So the next steps for MXL, in September 2025, the European Broadcasting Union, along with the Advanced Media Workflow Association, or AMWA, got together to create a joint task force on the dynamic media facility to ask some of the higher level questions above just the media exchange layer, things like further developing timing models, establishing a business level advisory council so that the business of dynamic media facility can move forward, and also addressing some of the orchestration challenges of those containers through some of the Advanced Media Workflow Association's existing knowledge and their networked media open specifications, or NMOS. And the MXL first V1.0 release candidate was published on December 25th, Western Christmas 2025, and we're about to have the first release coming up likely before NAB. And the MXL Fabrics API, they'll be doing that RDMA. Again, we think that's coming soon. I think that will also probably be before NAB 2026. So thank you very much for your attention. If you're interested in more information, the European Broadcasting Union has an MXL page. And also, of course, we're on GitHub with the GitHub MXL project. Thank you very much.
Thank you. Questions for the audience?
Just list some of the network interface cards that support that. I think you mentioned the NVIDIA XL, but what set of network interfaces will actually be able to use with this?
Yeah, so on-prem, it's likely going to be any card that supports RDMA over Converged Ethernet or RoCE. So I know ConnectX from NVIDIA definitely does that. I'm sure Intel has one that supports that as well. On the cloud, we have the elastic fabric adapter. So yeah, that's available now on EC2 instances, so you can use that as well. There's also Ultra Ethernet, which is coming on-prem probably within the next year or two, so that might be something else to watch out for. That's probably a bit more advanced than Rocky, so I think Ultra Ethernet is something to watch out for.